Why is one of the world's most powerful materials also one of the most dangerous? Imagine a material so powerful that it can light up cities or destroy them in seconds. This is uranium, the heart of nuclear energy. But raw uranium isn't enough. Only enriched uranium can power reactors or weapons. Today, we dive into the fascinating, complex journey of how uranium becomes enriched. 1. The birth of uranium, nature's hidden treasure. Our story begins deep underground. Uranium is a naturally occurring element found in rocks and soil. Most uranium mined from the Earth is the isotope U-238, which is stable but not very useful for nuclear reactors or weapons. Only about 0.7% of natural uranium is U-235, the isotope capable of sustaining a chain reaction. Think of it like searching for a few golden grains of sand in a massive desert. Before uranium can be used to create energy, it must undergo a transformation, a process called enrichment. Without enrichment, the energy locked in uranium remains largely untapped. 2. Mining and milling, extracting the raw material. The first step is mining uranium ore. There are two main types: open pit mining and underground mining. Open pit mining involves removing large layers of earth to reach uranium deposits, while underground mining uses tunnels to access deeper ore. In some countries, uranium is also extracted through in situ leaching, where chemicals dissolve uranium directly in the ground. Once extracted, the uranium ore is crushed and chemically treated in a process called milling, producing a concentrated powder known as yellowcake due to its yellowish color. This powder contains mostly U-238, but still only about 0.7% U-235. At this stage, it's still not ready for reactors or bombs. It's just the raw starting point. 3. Conversion. From powder to gas. Here's where the transformation starts. Yellowcake is converted into a gas called uranium hexafluoride, UF6. Why a gas? Because uranium enrichment relies on separating isotopes based on their tiny mass differences, and gases allow this separation. The conversion involves chemical reactions in tightly controlled plants. UF6 is a highly reactive, corrosive gas, so safety is paramount. Workers wear protective gear, and the plant is designed to prevent leaks. It's like handling a sleeping dragon. You must be precise, or chaos could erupt. 4. The principle of enrichment, separating the rare from the common. Enrichment is essentially a game of separation. Remember, natural uranium has only 0.7% U-235. Most enrichment processes aim to increase this percentage depending on the purpose. Low enriched uranium, LEU, 3 to 5% U-235, used in nuclear power plants. Highly enriched uranium, HEU, over 20% U-235, sometimes up to 90%, used in weapons. There are several ways to achieve this enrichment, but the most common are gaseous diffusion and gas centrifuges. 5. Gaseous diffusion, the first giant step. Gaseous diffusion was one of the earliest enrichment methods. UF6 gas is forced through a series of porous membranes. U-235 atoms, being slightly lighter than U-238, pass through the membrane slightly faster. Over thousands of stages, the concentration of U-235 gradually increases. Imagine trying to separate a few feathers from a pile of sand using hundreds of sieves. It's energy-intensive, slow, and requires massive machinery, but it works. In fact, this method powered much of the early nuclear programs in the mid-20th century. 6. Gas centrifuges, spinning to perfection. Modern enrichment mostly relies on gas centrifuges, which are far more efficient. Picture a spinning tube. UF6 gas is introduced, and the heavier U-238 moves toward the outside, while the lighter U-235 concentrates near the center. By carefully extracting gas from different zones, scientists gradually increase the U-235 concentration. Centrifuge cascades are connected in series and parallel, sometimes numbering in the hundreds or thousands, to reach the desired enrichment level. This method uses much less energy than gaseous diffusion, making it the backbone of today's nuclear industry. 7. Laser enrichment, the cutting-edge frontier. While centrifuges dominate, research continues into laser enrichment. This technique uses lasers tuned to ionize U-235 selectively. Once ionized U-235 atoms can be separated from U-238. It's highly precise and could revolutionize enrichment, but it's also extremely sensitive technology, heavily controlled worldwide. Think of it as picking out specific grains of sugar from a mix using a laser pointer. It's SCI-Fi level precision in real life. 8. Safety and security. Handling a double-edged sword. Enriched uranium is powerful but dangerous. Plants are designed with multi-layered security and radiation shielding. Workers monitor radiation, temperature, and pressure constantly. Accidents can release harmful radiation, so procedures are strict and technology is advanced. On top of physical safety, enriched uranium is also a national security concern. HEU can be weaponized, so enrichment facilities are under international scrutiny. Organizations like the International Atomic Energy Agency, IAEA, ensure that uranium is used for peaceful purposes. 9. From enrichment to use, fueling power, or creating danger. Once uranium reaches the desired enrichment, it's converted into fuel rods for reactors or into weapons material in highly classified environments. In nuclear reactors, enriched uranium undergoes fission, splitting atoms and releasing massive energy, which is converted into electricity. For weapons, enrichment must reach extremely high levels, and then the uranium is shaped into devices capable of chain reactions. This is why controlling enrichment technology is critical. Same science, but drastically different consequences depending on use. 10. The global perspective, a complex web. Countries worldwide maintain enrichment facilities, each under strict rules. Some nations produce LEU for power, others secretly pursue HEU. International treaties, sanctions, and inspections all revolve around this technology because of its potential for both progress and peril. Interestingly, advances in enrichment are a story of human ingenuity and energy challenges. From the enormous gaseous diffusion plants of the 1940s to today's spinning centrifuges, it's a tale of mastering physics to control energy at the atomic level. 11. The environmental angle. Energy with responsibility. Nuclear power offers clean energy, but enrichment leaves a footprint. Waste, U, F6, and depleted uranium, mostly U-238, must be managed carefully. Modern programs focus on recycling and safe storage. In some advanced designs, depleted uranium can even be reused, turning waste into a resource, a full circle of atomic efficiency. 12. The fascination of enrichment. Science meets story. What makes enriched uranium fascinating is not just its energy, but the story behind it. It's a journey from the depths of the Earth, through chemistry and physics, into controlled, visible power. Enrichment is invisible, intricate, and dangerous, but it fuels entire nations. It's a human triumph and a cautionary tale in one. Conclusion. Next time you flip a light switch or hear about nuclear power, remember the journey behind that energy. From yellowcake in the ground to enriched uranium spinning at thousands of rotations per second, it's a story of physics, engineering, and responsibility. Harnessed correctly, it lights up cities. Misused, it can devastate them. Enriched uranium is not just a material. It's the story of human ambition, precision, and the power of nature tamed by science. Thanks for watching. If you enjoyed this video, don't forget to hit like, share, and subscribe for more updates.